it turns out that the sun is just a star, right? So there's also this historical speculation going thousands of years ago. What on earth are stars? No one knew. It was only in the last 100 years that we started to have a pretty good idea. On the right here is the furthest picture we've taken of the sun. Since 1990, turned its camera around and pointed it back towards the sun and took this nice picture where you begin to get a sense for the fact that the sun is just a star. You go far away enough, and it's a pretty ordinary looking star. Shorter talk about the die, and also we'll talk about how when they do die, they produce all of the elements that were made out of it. Right? If it weren't for the death of stars, we wouldn't be around. There wouldn't be planets there wouldn't be carbon. There wouldn't be the stuff, the kind of solid, normal terrestrial stuff is made out. All right, so let's first talk about the night sky and looking at stars and kind of surveying stars. Here's a picture, one example of one of the things you'll look up and see in the night sky. This is a constellation Cassiopeia. You see these five kind of sideways W-shaped stars. You see hundreds of stars in this photograph. Some are a little bit bluer than others. Some are a little bit redder. Some are brighter than others. And one of the topics of today is the fact that when you see stars that are brighter, especially these particular five that make up a constellation like Cassiopeia, I want you to begin to see things in 3 dimensions, right? These stars are not, as you might think, just little punctures on some sphere at some distance away. All these stars are vastly different distances from each other. And some are bright because they're close to us, but some are far away, but happen to be very, very intrinsically luminous. Overall, to go out on a night outside the city, clear night, you can see thousands of stars. Under the best conditions, the furthest you can see is about a couple thousand light years away with the naked eye. And to give some perspective, right, we talk about just like say the 25 brightest stars. The closest one to us is Alpha Centauri, about 4 light years away. It's one of the brighter stars because it's so close. The furthest is Deneb, so that's 2,600 light years away. That might seem far, but actually that's a tiny fraction of the distance to the edge of the galaxy. And now that's with the naked eye, but astronomers, as we'll talk about, have cataloged the position, the velocity, the brightnesses of over 1 billion stars. That's still only about 1% of all of the stars in the Milky Way. And kind of one interesting thing I do want to mention is that when we learn a tremendous amount, there is a tremendous amount we'll talk about that you can learn about stars. They're all just points of light. There's only a handful of exceptions. I'll show you a picture in a second. There's a handful of exceptions where we can resolve them and actually see their surface. But most of the time, they're just points of light. Here's a picture, an illustration of what our Milky Way galaxy looks like, where the sun is, and then a little circle representing our neighborhood around the sun. Of all the stars that you might see with your eyes in the night sky, it's actually just a tiny, tiny fraction of the stars in the Milky Way. Just the ones that are closest to us are the ones that we can see. It's a little bubble about 2,000 light years in size. Here's a picture showing the 25 brightest stars in the night sky. The brightest one is Sirius in the upper left. But one thing I want you to notice is that some are bluer, some are redder. We'll learn that has to do with their temperature. And as we'll talk about, some are much further away than others. And also, one thing, when you see pictures of stars, it does sometimes look like you could see more than just a point of light. But I want to emphasize that that's just an artifact of optics. In fact, these really are just points of light. And here, there's a few exceptions where with our best telescopes, we actually can resolve stars that are pretty close to us and that happen to also be really, really big. So some examples are Pi 1 Gruis here on the left, and Antares in the middle, Betelgeuse on the right. These are each about 500 light years away, so relatively close and really, really big, about 500 times the size of the sun. So that's why we can resolve them. But in most cases, stars We're just talking about points of light. Another thing I want to talk about before we talk about cataloging, like say the positions of stars, is the fact that, well, for thousands of years, people pondered about the fact that stars appear to move, right? Every 24 hours, they revolve around us. At least that's what it looks like. Here's a picture of star trails. This is if you take a long exposure photograph of the night sky over several hours, you see the stars are moving. They revolve around. This is taken in the southern hemisphere, so they're revolving around the southern pole. Northern hemisphere, they revolve around the star. And of course, people wondered, right? For a long time, people thought that the stars literally did revolve around the Earth, right? But we talked about how we now understand, well, the Earth is rotating. So it looks like the stars are moving, but really the Earth is rotating and the stars are fixed, right? We call this the celestial sphere, where the stars are fixed. And so in our lifetimes, in human lifetimes, the stars are fixed on the celestial sphere. But I do want to mention that, in fact, they are moving. So I want to talk a little bit about the fact that outside of human lifetimes, so over thousands of years, the stars do move. And so, for example, let's consider the closest star to us, Alpha Centauri. Here's an illustration of the trajectories in terms of how close they are to us of several star systems. Where on the bottom is where our solar system is in this gray area. Y-axis is distance to us. So, and the blue dotted line shows that right now, the Proxima Centauri and Alpha Centauri, they're part of a star system. They're the closest to us today, about 4 light years away. But over 10, 20, 30,000 years, actually, for example, Ross 248 is going to come and eventually eclipse the Centauri system as being the closest star to us. So over thousands of years, we do have to worry about these things, what's closest to us, and then also where the stars are in the sky. So actually, I want to illustrate, I'll use Orion, the Orion constellation, to illustrate the movement of stars. So remember, Orion kind of looks like this in the upper left, an illustration of the fact that you have the arms here on the top and bottom belt, the sword of Orion. And this also gives me a good opportunity to show that these stars in Orion are just a typical example where the stars, if you move into 3 dimensions, the stars are actually very far away from each other, right? So for example, Betelgeuse is relatively close, but some of these stars are really far away. With some of the modern methods that we'll talk about later in this lecture, we've been able to learn about how these stars are moving. Now, they're all moving in kind of random velocities relative to us, but the closest ones are going to be the ones that appear to move faster in our field of view. And so here, the Gaia telescope, which we'll talk about, has precisely measured the locations and velocities of stars in the night sky. And we can watch. We can do a simulation of over the next 100,000 years how they will move. So here's Orion. Here's Betelgeuse in the upper left. Here's Orion's arms and legs. And let's watch as Orion changes over 100,000 years. On the back. And so what you'll notice is that there's some stars that are really close to us in the foreground that are actually moving really rapidly, and they're all kind of moving in random directions. And then you also see that, for the most part, it's actually Betelgeuse, the upper left arm of Orion here, that's moving. You see his arms are kind of stretching. There's also a star coming in from the lower right. Move this away so I can, yeah. So you see there's a star moving in from the right that's going to actually be kind of part of the constellation of Orion in 100,000 years from now. See, it's moving in. So anyways, I want you to understand, have this picture in your mind, that the stars really are moving. But for the rest of our discussion of stars, we're going to assume, right, while you're going measuring stars in our lifetime, that they're roughly fixed along the celestial sphere. We're going to be cataloging them and measuring the properties. Any questions so far? So I mentioned this problem or observation that, when we see these stars, some are brighter. They look brighter because they're closer, but some are actually really far away, but happen to be intrinsically very bright, very luminous. And so we need to tease these things apart. We need to somehow figure out which stars are actually brighter, which ones are more luminous, compared to which stars just appear to be brighter by virtue of being closer. And so this is one of the central projects of studying stars. So first of all, some definitions, right? What is a luminosity of a star? Well, it doesn't even have to apply to a star. It can apply, for example, to a light bulb. It's the total amount of power, which is energy per unit time, emitted by something, right? So you're familiar with a light bulb, right? Say it's 100 watts. So the units here of luminosity are watts. That's energy per unit time, or power. And if you run a light bulb for 24 hours, that'll cost you something, right? Because it's emitting some amount of energy per unit time, right? So over time, you accumulate an energy cost. So when we talk about luminosity, things can have more or less luminosity. You have a 100-watt light bulb that emits half the power as a 200-watt light bulb. It's half as bright. The sun has a really high luminosity, okay? 4 times 10 to the 26 watts. It's almost hard to imagine how large that is. It's about a trillion times greater than a 100-watt light bulb. Okay? Now, before I ask you an actual poll question for you to answer, right? Let's just kind of make sure that we're on the same page here. This is something that people often get confused about, right? What are the standard units of luminosity? Well, remember, it's energy per unit time. Some people do have a habit of saying watts per second, because they're thinking something per unit time. Watt is a unit of energy per time. Okay, watt actually is technically a joule, which is the unit of energy per second. Watts are the units of luminosity. Okay. Now, the solar luminosity, which we represent as, right, as you've seen before, that's the symbol for the sun. So luminosity of the sun is 4 times 10 to the 26 watts. And in our study of stars, we're going to understand that some stars are much more luminous or much less luminous than the sun. There's an upper limit. It's called the Eddington limit. A star cannot be much more than about 1 million times more luminous than the sun, 10 to the 6. Okay, so all stars tend to be less than about 1 million times as luminous as the sun. Anything more luminous, and they actually literally blow themselves apart. Okay, we're going to see an example of that in a second. The least luminous stars can be about a 10,000th of the luminosity of the sun, and that corresponds to just very small stars that are not burning through their fuel very quickly. Okay, dim stars, these smaller stars, are much more common than bright stars, but it turns out that you don't see them as much because they're hard to see. They're not as bright. Here's an example of a star near the absolute maximum possible luminosity called Eta Carinae. It's located in this homunculus nebula, which was formed when it underwent kind of a major explosion 150 years ago. Now, this is 7,500 light years away. So remember, with the naked eye, you normally wouldn't be able to see a star that's 7,500 light years away. But it's a very young star, very, very massive star. Massive stars, as we'll learn, burn through their fuel in just a matter of 1 million years. So actually, the star is potentially going to go supernova, and that's something we'll talk about in our lifetimes. But it's one of the most massive stars that we studied, and it came to our attention through this enormous explosion that generated this nebula in 1843, such that this star, 7,500 light years away, briefly became the second brightest star in the sky. And our understanding is that this star was just above the Eddington limit, meaning it was unstable. It kind of blew itself apart because it was too massive and it was generating too much energy. So actually it blew off about 30 sun masses worth of mass into this nebula. So now it's just below the Eddington limit. It's about 1 million times as bright as the sun. And it's underwent a few more explosions because it's still kind of unstable. It's about 24 times the size of the sun. Anyways, this is one of many examples that we see of stars near the maximum possible luminosity. On the other end of the spectrum, we have a very close, a very nearby star, actually a three-star system. Alpha Centauri A, E, and E, also known as Proxima Centauri. Proxima Centauri of energy per unit time it does. Why is the star more or less luminous? Well, I've introduced you before of black body radiation. All objects, technically objects that are black bodies, basically any ordinary object, emits light. Right? You and I, we are emitting infrared radiation. Stars emit light, and how much light they emit is given by the Stefan-Boltzmann law. The luminosity is proportional, so it's just a constant. I don't expect you to know the Stefan-Boltzmann constant. Proportional to the area. That makes sense. The surface area of something is larger, more light is emitted. Okay? So larger things emit more light, and things at a higher temperature emit more light. That's the Stefan-Boltzmann law. So a star that's larger or a star that's at higher temperature is going to emit more light. And we often, what you'll often see is we compare the luminosity of something to the sun. Okay, so we give the luminosity in units of how luminous the sun is. And so here, I'll just do a little math. If we were going to compare the luminosity of a star to the sun, that is it twice as luminous as the sun? Is it a tenth of luminous as the sun? What does that depend on? Well, we can plug in our Stefan-Boltzmann law for the star on the top and for the sun on the bottom. And what does the area of a star or the area of the sun depend on? It depends on the radius. Okay, the surface area of a sphere goes as 4 pi r squared. So I'm plugging in 4 pi times the radius of a star squared over 4 pi times the radius of the sun squared. And canceling out these constants from the top and bottom, we end up seeing that how luminous a star is compared to our sun depends on two things. It depends on how much larger or smaller it is compared to the sun. And that goes as the square. So for example, if a star is twice as large as the sun, then all else being equal, it will emit 4 times as much light. And the other thing is how hot the star is compared to the sun. Say if it's twice as hot as the sun, it will emit, so it's going to the 4th power here, it'll emit 2 times 2 times 2 times 2, or 16 times as much light. So just doubling the temperature of a star gives you 16 times as much light. So this is the ending of what gives luminosity. And before I go any further, let's do one of our poll questions. How you're doing here. So I want to ask you, what is the luminosity of a star? And then we'll go over it if you have, depending on how you do. Hold on, let me move this out of the way. All right, everyone, a Zoom poll question. So what is the luminosity of a star? Is it the apparent brightness of a star? Is it surface temperature? Is it its lifetime? Is it the total amount of energy it emits over its lifetime? Or is it the total amount of energy that star radiates each second? Let's make sure we have this concept of luminosity down before we move forward.
I think it's this one then, because it's so-called watts. This one.
Okay, I think I'll give you about 10 more seconds to input your answers. Okay. So, sharing the results. So, So there are two answers, one of which is right that people focused on. Some people said the luminosity is the apparent brightness of the star in our sky. And actually, this comes to something we're going to talk a lot about in a second, which is distinguishing apparent brightness from the luminosity. So actually, no, answer A is wrong. A is how bright a star appears, but that's different from the luminosity, which is E. It's the amount of energy that the star radiates each second. And what's different is how far away the star is, right? How bright a star appears depends on the distance. So that's something actually we're going to have to talk a lot about. Okay, so for this question, the answer is E. Luminosity is just the total amount of energy in light the star emits per second. It's its intrinsic brightness as opposed to its apparent brightness. Are there any questions about that before we continue? So we're just getting to this concept of brightness. So you're all whose headlights have a fixed luminosity, right? The headlights are not getting brighter. They have a fixed luminosity, but the car is getting closer to you, so it appears brighter, right? As it gets closer to you, its headlight gets brighter and brighter. That's its apparent brightness. Depends on distance, right? So the luminosity and apparent brightness are distinguished by distance. So let's think of this, for example, right? Which thing appears brighter? Alpha Centauri, that's the closest star to us, or the sun? Which one appears brighter? They actually have a similar luminosity. But of course, the sun appears brighter, even though in fact, Alpha Centauri, they have similar luminosities, but Alpha Centauri has slightly more luminosity than the sun, but it's further away from the sun. So it's just a tiny point of light, whereas the sun, of course, is very, very bright. So brightness is different from luminosity, okay? And how do we understand how brightness depends on distance from us? Well, imagine you have a star, right? It's emitting light in all directions, okay? So we're just like the sun in the center of some imaginary sphere. It's emitting light in all directions. How is that light getting diluted as you get further and further away? Well, you can imagine that light gets spread out over some imaginary sphere. And we call the apparent brightness is the total luminosity, it's the total energy emitted by the star per unit time, divided by the area of that imaginary sphere that's diluting all that energy. The energy is getting spread out over that sphere. And the surface area of the sphere goes as 4 pi r squared. So therefore, the apparent brightness goes as the total luminosity divided by 4 pi r squared. In other words, the brightness decreases as the square of the distance go away from something. That light is getting diluted over the square of the radius, the area of an expanding sphere as you get further and further away from something. So that's an example, right? Consider 2 light bulbs, okay? Here's a light bulb that is 50 watts, and here's a light bulb that's 4 times as luminous. It's a 200-watt light bulb, okay? But the 50-watt light bulb is, say, 1 meter from you, and the 200-watt light bulb, even though it's 4 times as luminous, is 3 times as far from you, 3 meters from you. Well, using this formula, we can work out which one, is going to be the most bright in its appearance. So even though this one's 4 times as luminous, it's actually going to be about half as bright because it's 3 times as far. And remember, the brightness goes as the square of the distance. So the brightness goes down by a factor of 3 squared, or 9. So actually, even though it's 4 times as luminous, 4 divided by 9 is about half as bright as that 50-watt light. Okay, and so this is how we understand stars. This is how we relate the distance of stars away to its apparent brightness to its luminosity. And astronomers sometimes solve for so you can take the same equation and solve for L, solve for the luminosity. So if you know the apparent brightness and you know the distance, you can figure out the luminosity of a star. Or if you know the luminosity and you know the apparent brightness, you can solve for the distance of the star. These are some of the main tools astronomers use to figure out, you have how bright a star looks, you have its distance, you can figure out its actual luminosity. So here's another, so we'll go through this together, right? Just to make sure you understand this concept that suppose we're looking at a star. So we gave light bulbs as an example a second ago, but suppose we're looking at a star and imagine that we doubled our distance from that star. Okay, everything remains the same about the star, but we've doubled our distance from the star. What happens? Okay, well, the luminosity of the star remains the same, right? The luminosity of the star is just how much energy the star is emitting. That doesn't care about how far away we are from the star. The luminosity is the same. What does change is its apparent brightness, okay? If we go twice as far away, the apparent brightness decreases as the square of that distance. In other words, twice as far away, 2 squared is 2 times 2, or 4. 4 times less bright. Another place people sometimes get tripped up is units. So what are the standard units for apparent brightness? So remember, let me go back to that formula. Brightness is luminosity, which is watts, remember. Brightness is watts per distance squared, or meter squared. So the units for apparent brightness as opposed to luminosity are going to be watts per square meter. Any questions so far? So going back thousands of years, people didn't have a way of measuring the luminosity of stars because they didn't know the distances to stars. But one of the first to kind of systematically create a star catalog was Hipparchus, about 100 BC. And Hipparchus divided stars into 6 what are called magnitude classes. Okay, we use lowercase m. Magnitude 1 stars were the brightest stars, and magnitude 6 stars were the faintest stars that could be seen with the naked eye. And we've adopted this system. So we've taken this system from ancient times, and we use a modern definition that fits that, so that the star catalogs from thousands of years ago can remain more or less the same. So the modern definition, so it turns out that the difference between the brightest stars and the faintest stars we can see with the naked eye is about a factor of 100 in brightness. So what we've done is we said, okay, we'll represent the brightness of stars with this letter M, and every 5 steps will change the brightness by a factor of 100. Okay, so if you go 5 steps, you go a factor of 100 in brightness. If you go 10 steps, you go another factor of 100. So 100 times 100 is 10,000. So every 5 steps is a factor of 100 in brightness. You can go steps up, which go to less bright, or steps down that go to more bright. And so what this means is each step, by the way, is changes by a factor of 2.5. Okay, so if you go to a step star of magnitude 3 to a star of magnitude 4, the magnitude 4 star is 2.5 times less bright than the magnitude 3 star. So this is our system for talking about apparent magnitude or apparent brightness. Here's just some examples. So going here to say the limit of the naked eye, that's 6. So naked eye limit, looking at outside of a city, far away from lights, you can see stars of magnitude 6. You can't see stars of magnitude 10, but you just barely can with binoculars or a cheap backyard telescope. Pluto, for example, is magnitude 15. That wasn't discovered until relatively recently because it's so hard to see. And the best telescopes can see up to magnitude 30. Remember, going up in magnitude means dimmer and dimmer. If we go the other way, we can actually go to negative numbers because the way the system works, if we just go towards negative numbers, each time we go a step of 5 in this direction up here towards the negatives, we just are changing the brightness now up by factors of 100 every 5 steps. So actually Sirius is -1, very bright. Some of the planets like Venus can be brighter than that, like -4. The full moon is -12. magnitude, so we're getting really bright. And the sun, of course, is by far the brightest. It's a apparent magnitude of minus 26. Now, here's the list of the 10 brightest stars, showing some of their characteristics. We'll talk more about class of star in the next lecture. But here are their distances. And one thing you'll notice is that the brightest star, Sirius, is about 8 light years away. The next brightest star, 300 light years away. The next brightest star, Alpha Centauri, only 4 light years away. In other words, the second brightest star is much further away than the third brightest star. So what this tells us is that we can't tell just by looking how far away a star is. Some stars are just way more luminous, like Alpha Carinae, Canopus. And so even though they're further away, they can be very, very apparently bright, have a very bright magnitude. Now, here's another question. So here's a poll question for you. So remember this sort of picture, right? When we're talking about stars, brightest star, -1 magnitude. The faintest stars you can see with the naked eye, about +6. So just to make sure you're following along, let's ask a poll question. What's the faintest star visible to the naked eye in magnitude? Okay, what's its magnitude? Let me get up the poll.
Wouldn't it be B then? It would be B. Should be B. It should be B. What the naked eye is 0.6, so I think it should be.
Give you about 10 more seconds. All right, stopping it. Okay, and good. Most people said 6. This is kind of a memory test, but it's just the sort of thing that I want you to remember for the quizzes. So faintest star you can see,
6.
about 6. Brightest star is -1. And when you're looking out at the sky, right, one thing you can correlate these magnitudes with is how bright the sky is, which is, in other words, what's the viewing quality where you can see these sort of stars. So if we go and consider, say, magnitude 7, that's just beyond the visible limit. There's about 15,000 stars in the sky above magnitude 7. Okay, but you can't see that many unless you have really good eyesight. Most people can see about 5,000 stars, and that's when you're really in the middle of nowhere. You can see, we talked about the zodiacal light. You can see the zodiacal light from reflection of sunlight off dust orbiting the Earth. If you get just maybe not perfect viewing conditions, but pretty good, you can see magnitude 5 stars. You can see the faint Milky Way. See about 1,600 stars. If you're in the suburbs, maybe you can see about 500 stars. That's magnitude 4. In a major city like Chicago, in your backyard, maybe you can see a few hundred stars. That's a magnitude 3 and above. And in the worst case center of large cities, maybe you can see a few dozen stars. That's magnitude 2 and above. And just again, for comparison, Sirius is -1. And the planets are brighter than Sirius. Okay. Well, Venus, Mars, for example. And if you're a star watcher, you're concerned about this, right? What's the viewing quality? So here's a satellite image of the United States taken at night, where you can see all the cars and city lights kind of showing up, giving you a nice outline of the United States. You can kind of see that the Chicago area has lots of lights. It's pretty bad for star viewing in the Chicago area. And in fact, star watchers have created these maps that give you a really good indication of not just qualitatively how good the viewing conditions are of the sky, but actually quantify exactly how bright the sky itself is. So this is called This is the color here is a measure of what's called the sky brightness. If you look straight up, the zenith sky brightness, and it's given in magnitude per arc second. Okay? So look at a little portion of the sky. What's the magnitude of the background light that's making it difficult to see stars? Okay? And you see that the Chicago area is pretty bad. If you've never been out to the middle of nowhere, go camping. I think that you might be surprised just how wonderful it is to just. It might sound boring, but this is why I got into science. I was just staring up at the stars in the sky, and it kind of gives you this sort of philosophical feeling, right? What's my place in the universe? It's kind of amazing in this age of YouTube and everything. If you look at a really dark night sky, it's kind of entrancing. You can just watch it for hours looking for a shooting star. Now, we talked about apparent magnitude of stars. We need to talk about how we get from there to that luminosity of the star, or alternatively, what's some absolute measure of the magnitude of the star? And so, where apparent magnitude we give lowercase n, and say the sun, for example, its magnitude is -26, right? Very, very bright, apparently. If we want to consider an absolute version of magnitude, what we do is we take the apparent magnitude, but then we figure out what would the apparent magnitude be if we imagine placing that star 10 parsecs from us. 10 parsecs is about 32 light years. We'll talk about parsecs later on in this lecture. That's about 32 light years. In that case, the sun has an absolute magnitude of 4 or 5, which is not so impressive. It's pretty ordinary. Okay? So this is how we take apparent magnitude and turn it into absolute magnitude. We imagine, what if all the stars were the same distance from us? Then how bright would they be? Okay, that's absolute magnitude. And we can work out then from that. Now, I don't expect you to memorize this formula, but we can work out from that exactly how far a star is based on the difference between its apparent and absolute magnitudes, or vice versa. If you know its apparent and absolute magnitude, you can figure out the distance. What I do want you to be able to do, though, I don't expect you to do a calculation here, but on a quiz, for example, I do expect you to say, hey, if one star's apparent magnitude is, say, less than its absolute magnitude, what does that mean? Okay. So let's work through an example like that. So like the star Vega, for example, has an absolute magnitude of about 4. Okay. It has an apparent magnitude of about 0. What can we conclude? So think about it in terms of, okay, its apparent magnitude is 0, but if we were to move it to 10 parsecs away, its absolute magnitude would be 4. What does that mean? Well, 4 means less bright. Okay? So if we were to move it to 10 parsecs, it would be less bright. Therefore, Vega must be closer to us than 10 parsecs. Okay? Because if we move it away to 10 parsecs, it gets less bright. So we can conclude, based on thinking about what these definitions mean, is that Vega is nearer than 10 parsecs from Earth. Okay? So this is the level at which I expect you to understand absolute and apparent magnitude. Are there any questions about thinking about this? Okay, so how do astronomers figure out the distance to stars, right? If we want to understand, given the apparent brightness of a star, what its absolute magnitude is, or what its luminosity is, we need to know its distance. So this is a central project of astronomers, and we do it using parallax. So you're all familiar, even if you're not familiar with the term, you're all familiar with the concept of parallax. That is, if you're, say, driving by, you're driving on the highway, there's mountains in the distance, but things closer to you are flying by, right? So here's an example of a grain silo, right? You're driving, the mountains aren't moving, but the things that are closer to you, like this grain silo, are moving. And the things that are closer and closer to you are moving by faster and faster, okay? That's the concept of parallax. And we can use that. So astronomers, when you look at, say, a grain silo here and a grain silo here, you can calculate that as an angle, right? Remember we talked about angles in the sky, right? If you put your fist out, 1 arm's length, that's about 10 degrees. okay? You can measure the angle that something moves in the sky, and we need to relate that somehow to a distance, figure out how far away it is. So we went over this before, but I want to remind you a little bit about how you relate angles to distance. So the way I'm going to do this is consider a circle. We all know that the circumference of a circle is 2 pi r, right? If we have a circle, its radius is r. Imagine going all the way around the circle and measuring how long that blue line is. It's 2 pi r. Now, what we want to use as astronomers is some fraction of that length, and that's called an arc length. So if you go all the way around, you might call it 360 degrees. That's an arc length of 2 pi r. If you go all the way around, 2 pi r. But suppose you only went halfway around instead of all the way around. So you went only 180 degrees. What's your arc length then? Well, it's half of 2 pi r. Okay. Half of 2 pi r. If you go a quarter of the way around, it's a quarter of 2 pi times r is your arc length, right? A quarter of a full circumference. And so this concept is where radians come from, okay? This angle measured in radians can be used to, and that is a fraction of 2 pi. That is, you go all the way around, it's 2 pi. Halfway around, it's 1 pi. So as a fraction of 2 pi, that's a radian. And we have this nice relationship. The arc length is the angle times r. So it's a really nice relationship between this distance, and the angle. And this is what astronomers use to find the distance to stars. In practice, we just rearrange it like so. We want to find the distance r to a star. We need to know the angle theta and this distance s, okay? And in practice, now, so I derived this equation by talking about an angle being measured in radians, but both you and also astronomers actually like to use degrees. So there's 360 degrees for every 2 pi radian. So we need a conversion factor. So if we want to
Get out of here! Go your room, go your room!
360 degrees for every 2 pi radians.
I'm in class, go
And
your
in fact,
room. Are you done with
astronomers don't
school?
even like to use degrees because remember, a degree is pretty big. You put your finger
Oh, at
out,
12:30. It's
that covers about a full
12:14.
degree in the sky. We're talking about tiny little distances.
Go your room.
Watching stars move.
I'm in class, go your room.
Astronomers like to use arc seconds. That's a 60th of a 60th of a degree, or 3600th.
Hey, baby, go your room, baby.
So then you get to our final formula.
Why are you sitting on your friend? Go your room.
How far it is.
Go your room.
This is a factor here.
Mama.
3600 over 2.
Go your room.
And S over the angle measured in 4 seconds gives us a distance to a star. How exactly do astronomers
What the heck?
use this? Okay. We leverage the fact that
Yeah,
over
ba.
the course of a year, the Earth is moving around the sun.
Ayo, sing
The
sing
Earth
naman.
is moving, say from June to January, over 6 months. It's moving from one side of the sun to the other. So we can wait a few months
No, I want to
and
go
wait
phone
for
and go play with her.
Earth to move an astronomical unit.
The heck is this?
Earth-sun
Choke your
distance.
friend?
And then we measure, right? Remember, just like a grain silo, things closer to us, stars that are closer to us, will move further against background stars.
Oh.
And so the more something moves in angle, so this is the angle that we call the parallax angle, the closer something is to us. And this is the formula we use. So we wait a few months, the Earth moves 1 astronomical unit, we find how much a star moves in arc seconds, we multiply by this conversion factor, and we find how far the star is away. And here's the sort of calculation. So this is where the unit parsec comes from. It's the distance at which a star has a parallax angle of 1 arc second. That is, if you wait a few months, the star moves in the sky by 1 arc second. That tells you that the star is how far away? Well, it's calculated. 1 astronomical unit divided by 1 arc second is our angle, times this conversion factor, gives us 206,000 astronomical units for every arc second. Well, if I convert 206,000 astronomical units into light years, I get, if a star moves 1 arc second, it's 3.2 light years away. And because this is the units that astronomers like to use, arc seconds, astronomers just call this a parsec. P for parallax, rsec for arcsecond. So a parsec is a parallax arcsecond, and its distance is 3.2 light years. And this has the great use that if you measure a star to have a parallax angle of P, say, in arcseconds, you can measure the distance to that star in parsecs by just taking 1 over P. And this is the formula I expect you to know. Okay, I don't expect you to know all of this here. I just want you to know the distance in parsecs is 1 over the parallax. That's what astronomers use to calculate how far a star is. So for example, if you wait a few months, Earth moves around the sun, you see a parallax angle, a star shifts in the night sky by 0.04 arcseconds. You calculate how far away it is. D equals 1 over P. 1 over 0.04 is 25 parsecs. Okay, that's the unit astronomers like to use. Parsecs. 1 parsec is 3.2 light years. So for example, let's do just a couple examples, right? So for example, Sirius, Alpha Canis Majoris, has a parallax angle of 0.38 arcs. These are real numbers, 0.38 arcseconds, okay? While Procyon, Alpha Canis Minoris, has a parallax angle of 0.29 arcseconds, okay? First thing I want you to know is just which star is closer. Well, remember, the closer stars to the most is closer. It has a larger parallax. Right, remember, you can just think of those grain spirals. You're driving by something far away from angular movement compared to closer.
Give me back my phone.
And as an example of actually numerical distance, here's another example.
Get
Starting with a
out.
parallax angle of 1/20th. 1/20th of an arcsecond, which is 0.05 arcseconds. What's the distance to that star? Well, this is a nice application of that formula. It shows that it's actually not so hard. You just plug in 1 over P. P is 1/20th. What is 1 over 1/20th? Or 1 over 0.05? It's 20. 20 parsecs. So the distance to the star is 20 parsecs. And these are real examples. This is
Go your room, man.
stars and begin to create a.
Bad boy, go your room. You're gonna kill him.
I'm going to pause just to give you time if anyone has any questions.
Why you never 12:30 is 12:19. Get out of here!
Scientific instruments we have.
Get out! Hey, you get out here!
So, right, so Hipparchus, 2,000 years
Get
ago,
out!
was one of the first to do a systemic catalog of stars, but he didn't have the ability to measure, right? You need much more precise instruments than the human eye to measure these parallax angles. So what we've done, starting in the 1980s, is sent up, actually it's the counterpart to NASA in Europe, the European Space Agency, sent up the Hipparcos satellite, that's named after Hipparchus, to do astrometry. That is, it precisely measures the positions of stars. And that allows us to calculate their distance based on, right? I mean, that if we know their apparent luminosity, apparent brightness, and we know the distance, we can find their actual luminosity. Okay. And so by measuring the precise positions of stars over a year, we can get their parallax angles and get their distances. Further than that, if we see their movement, we can also measure their movement due to they're actually literally moving in addition to the parallax angle, and that allows us to get their velocities. I'll give an example of that on the next slide because so first of all, the Hipparchos satellite.
You go to your room now. I'm in class. Get out! Get out!
1990s.
Oh my gosh!
It could
Get
measure
out!
precision down to about 0.00.
Get out of here when?
And the successor to Hipparchus is Gaia. And this is kind of all the rage now. It was launched in 2000.
Get out, Malware! Get out! Get out!
We can measure parallax angles to 0.0002 parsecs. And as a result, it's been able to measure the positions of over 1 billion stars in the Milky Way. That's still only a small fraction of all of the stars in the Milky Way.
Get out, man.
It's actually a huge amount of stars relative to just 10 years ago. Here, I can show you a video of, so not only do you know the distances to stars, but if you watch them over years, you can get their velocities. So I showed you that kind of video of Orion earlier. Here, I can also show you a video of from Gaia of kind of stars in the night sky. If you're looking up towards the Milky Way over the course of hundreds of thousands of years, you can kind of map out how the night sky will change. Okay? And we can do this with precision for literally 1 billion stars based on the data from the Gaia satellite. Okay, and then the link's there, so if you want to watch more of that, the link is in the slides. Now, we're going through a number of things that allow us to determine a tremendous amount about stars just from looking at these points of light. So we talked about the luminosity and the brightness and how we need to know the distance to those stars to determine their actual luminosity and relate that to their apparent brightness. Another thing we can learn just by looking at these points of light is the temperature of stars. In fact, we'll even talk about the composition of stars a little bit today. This has to do with their color. So the hottest stars are kind of bluish color. They can be about 50,000 degrees on their surface. The coolest stars are kind of redder colored, about 3,000 degrees on their surface. Our sun is kind of in the middle. It's kind of a yellowy white, about 6,000 degrees on its surface. Most stars in the Milky Way happen to be smaller stars that are cooler and dimmer than the sun, but most of the stars you see in the night sky, we'll talk about next lecture what I mean by main sequence. But most of the stars that you see in the Milky Way in the night sky are much larger, much hotter, and brighter than the sun. That's just because those are much easier to see because they're so much more luminous. Now, how do we measure temperature? So I'm going to remind you of the Stefan-Boltzmann law, right? How higher temperatures correspond to greater luminosity. We're going to do a reminder also of Wien's law, how higher temperatures correspond to objects emitting shorter wavelengths of light, that is, emitting more bluish colors of light as they get hotter. And how when we look at stars, we can put the light through a prism and get the spectrum, right? We talked all about spectrum when we talked about light, and you can kind of get all the colors of the rainbow coming from a star, which tells you about their temperature and their composition. And we'll talk about how astronomers can precisely measure what we call a color index for a given star. So let me remind you about black body radiation, and this applies to stars. The hotter something is, and the larger something is, the more light it emits, right? The more luminous it is. We talked about that already. But in addition to the amount of light, depending on the temperature and the size of the star, the color also depends on the temperature, right? So this is called Wien's law. That is an easy way of quantifying what the peak, if we talk about this, these are examples of spectra. It's a continuous spectra for different stars. That is, it includes short wavelengths, so bluer colors of light, all the way up to longer wavelengths, including infrared on the right. But it peaks somewhere, and the peak is determined by the temperature. Okay, Wien's law says that the peak wavelength times the temperature is a constant. And in other words, if the temperature goes up, the peak wavelength goes down. Smaller wavelengths correspond to bluer colors. So if we apply both Wien's law and the Stefan-Boltzmann law, we get a picture like this. So you have like a hot star, it's kind of red. So it peaks kind of, say, here in the red. If you get a hotter star, it not only is emitting more light, so this spectrum gets higher in this plot, but it's also shifted to the left. It's looking yellower. You get it hotter still, it shifts more to the left, and the peak gets higher. It's getting bluer and more bright. Okay, this kind of is most of the story we need to understand when we look at the color of a star what his temperature is. Just remember, just stepping back, right? We are all emitting light right now, right? Remember, we are emitting infrared light. You don't see it unless you use a thermal imaging camera, but we're at room temperature, and we use this law to see. This Bean's law, we see that we're emitting infrared light. If you heat up a fire poker, at first it's emitting red light, infrared, but you heat it up enough, it starts to glow red, right? And it's brighter. You heat it up some more, it starts to add some yellows, right? Starts looking orange, then starts to add greens and blues, and it doesn't look green or blue because now it's emitting all the colors of the rainbow and it looks white. It starts to glow white hot, right? And that's like our sun. Okay, our sun kind of glows white hot because it's emitting all the colors of the rainbow. Although remember, the sun peaks in green. Okay? You can get hotter stars still that peak in blue, and then you can have stars that are emitting lots of ultraviolet even, and it look blue. Okay, so this is what leads to when you look at stars through a telescope, you can put a prism to take that starlight from that point of light and look at the full continuous spectrum of light coming from that star, and it looks like this. Okay, from the hottest stars, which we call type O, and I'll talk to you about where that comes from, down through the coolest stars that we call type M. The coolest stars you see emit a lot of red light. The hottest stars emit a lot of blue light, but it's all continuous spectrum. And here's the same sort of plot, but it's a little bit, just the colors are maybe a little bit exaggerated, so it's a little easier to see that the hotter stars, you'll see a spectrum that looks like this. If you look from left to right, that is a lot of blue, so the stars will look blue. Here the sun is in the middle. The sun, you'll see all the colors of the rainbow. Overall, it kind of looks white because remember, all the colors together make white. Whereas cooler stars, type M stars, are mostly emitting red. Now, just recall, right, when we talked about light, we talked all about spectral analysis. We talked about how you can have a continuous spectrum when you heat something up, right? There's a star emits a continuous spectrum of light. If it's hotter, it's shifted to the blue. If it's cooler, it's shifted towards the red. But in addition, remember that we learned about how every atom has a specific type of spectral line spectrum. And if you have a cool gas of atoms, like in the outer atmosphere of a star, that continuous light shines through those cooler atoms and they absorb light at specific spectral lines. So when we see the spectral distributions of stars, we not only see this continuous spectrum, but we see specific lines, these black lines, okay? Those correspond to what is in the atmosphere of stars, and stars are absorbing light based on what's in their atmospheres. And this was initially a big mystery. There was a hunt, and about 100 years ago, people were looking at the spectral, put starlight through prisms, looking at all these different stars, and they all look different, trying to understand what was going on. What did this tell us about stars? And so there's this really interesting story about the Harvard computer. So this is one of these first really, since the Hipparchus, really systematic attempts to map all the stars in the night sky by the spectra. So this was a new thing. It's looking at stars through telescopes with prisms. And in fact, a new thing that happened in the late 1800s was the ability to make photographic plates from telescope images. So you take a picture of a star through a telescope, create a photographic plate. You had a prism when you make.
I think it's still that lady that we saw earlier.
Dozens of stars, each with its own spectral line that you could use a magnifying glass to analyze. And the story is, at that time, there was a need for a lot of computers. Now, this term computer goes back way before electrical computers. The sort of machines we're talking, I'm using Zoom through. No, there's just people. People were computing. And at the time, you needed a lot of people to sort through these hundreds and even thousands of stars and analyze them. And so at Harvard, they hired a lot of women, mostly women, because they were cheap labor. This was a kind of a sad part of history, right? That they were paid less than men. And as a result, they were cheaper. And so at Harvard, they hired a lot of women to analyze stars. And they proved themselves to be meticulous astronomers, and actually some of them made a fantastic name for themselves as some of the century's best astronomers in their own right. So the catalog that was produced from the Harvard computers was the first of its kind, catalog of over 200,000 stars. And it's still used to this day. It's a famous catalog called the Draper catalog that we all still use. One of the first computer hired at Harvard is Wilhelmina Fleming. She analyzed about 10,000 stars, developed this first classification that we use these letters. So the letters of the alphabet, A, B, C, D, to characterize the spectral type of stars. And what she used was, she used the prominence of hydrogen spectral lines, okay, in stars. And for a reason I'll describe in a second, that was kind of confusing. No one understood really what the spectral line signified in stars at the time. This was still a mystery that was being unraveled. Annie Jump Cannon took that and made the connection between that and the temperature of stars and reorganized the letters. Okay, this is what's called the Harvard classification now that we still use today. And it goes O, B, A, F, G, K, M. This is the order that you're going to have to memorize, where O is the hottest stars and M are the least hot stars. You had Henrietta Swan Leavitt, who developed a relationship. She noticed that some stars get brighter and dimmer over a period of sometimes weeks or sometimes years. These are called Cepheid variables. And this was used, so she connected that to distance, or she connected that to distance because you could measure their luminosity based on how long it took them to become lesser or more bright. And Hubble actually used this later to, for the first time, determine that the Andromeda, what was at the time called the Andromeda Nebula, was actually a distant galaxy millions of light years away. In other words, this was the first time in history that people realized that the Milky Way was not the entire universe. Okay, really, this was a debate at the time. It was only after this discovery that we realized that the universe was way bigger and that there were actually distant galaxies millions of light years away, which kind of blew people's minds. Cecilia Payne was the first to establish what stars are made of. Okay, stars are made of mostly hydrogen and helium, right? We talked all about that. We talked about the sun, right? In fact, that's now we understand most of everything is made of hydrogen and helium, which we didn't understand at the time. So anyways, this is in brief the story of the Harvard computers, which is kind of a fascinating story involving some of the greatest discoveries in astronomy in the 20th century. By the way, I did want to just come back to this spectral type. So it was confusing. So it was labeled A, B, C, D for these spectral characteristics of stars. But the confusing thing was that understandably, cooler stars had weaker hydrogen absorption lines, but so did hotter stars. And that's because hotter stars, and they didn't understand this in the 1800s, hotter stars, the hydrogen is all ionized. So it actually can't absorb light as light from the stars going through it. So actually you had this kind of complicated mechanisms that weren't understood at the time. And for that reason, like A was given the first letter for stars that we now understand are actually kind of middle temperatures. Okay. So we now understand that the order is O is the hottest stars, M are the least hot stars. And actually, if you look at their spectra, it's actually a really complicated story of how you take, this is what was done by Cecilia Payne, unraveling what stars are actually made of, understanding those spectral lines, as opposed to the overall shifts in the continuous spectrum that characterize stars as temperature. Here's a picture of the Harvard computers with their magnifying glasses looking at a photographic plate. And this is what was done for hours on hours, analyzing these star by star, each of its spectrum, and then cataloging, creating a star catalog, finding the star, where the star is in the sky, what its brightness is, what its Harvard designation is. Okay? It's a letter assigned to each star. And so this Harvard spectral classification is still used today. So remember O for hottest star, M for least hot star. And you're going to have to remember this. So students since the 1920s or 30s have memorized this by using a mnemonic. So the historic mnemonic from the 1920s or 30s is, "Oh, be a fine girl or guy, kiss me." It was originally, "Oh, be a fine girl, kiss me," of course, which is dated to say the least, right? It's sexist. And so since then, right, we've now, depending on your preferences, said, "Oh, be a fine guy, kiss me." It's still kind of dated. But this is what astronomers still to this day use because it kind of sticks in your mind. "Oh, be a fine girl or guy, kiss me." So remember, OBAFGKM. There's been lots of attempts to come up with a better mnemonic. Here's just one example. "Only boys accepting feminism get kissed meaningfully." I encourage you to look up whatever you're most comfortable with or whatever sticks in your mind, okay? Because I will expect you on the quizzes to be able to tell me, if I give you 2 letters, tell me which one is the hotter star and which is the least hot star, right? O is hotter than B. OBAFGKM. In fact, in a few slides, I'm going to ask you to do this for a couple. So I'll give you a second to try to remember one of these mnemonics. While you're doing that, in addition to the correlating with the temperature of stars, I just want to mention a couple things we'll come back to, which is that the higher temperature stars happen to have higher masses. The lower temperature stars have much lower masses. This will also be connected to how long stars live and before they die. Higher mass stars burn through their energy much faster because they're hotter, and they live much shorter lives. So the mass is also related to their size. So hotter stars are larger, less hot stars are much smaller. And then finally, this tells you what fraction of the stars are these stars. So the hottest type O stars are actually a tiny, tiny fraction of all the stars. Most stars are type M stars, but again, we don't see them as easily because they're dim. We don't see dim stars as easily. Here's a spectrum of the sun and the spectrum of Arcturus. Just 2 examples to see what astronomers look at. This is the full spectrum of the sun. Now, if I were to unravel this, like if you took it through a prism, this would be really long and thin, but we've wrapped it around the page over and over again. So it starts up here at infrared, red, orange, yellow, green, blue, violet. Not only do you see the spectral continuous spectrum, but you see all these absorption lines, talking about all these kind of darker lines or absorption lines, telling us what's in the atmosphere of the sun. If I flip back between the G-type sun and K, so OBAFGKM, so G comes before K, so G should be hotter than K. And indeed, you see, if I flip back between these spectra, the sun, the G-type star, is bluer than the Arcturus. So if I go to Arcturus, you see it's brighter in the reds. So this is how we classify the spectrum of stars. And the way astronomers do this precisely is using a color index. That is, we look at, we take a telescope image of a star through, say, a blue filter, and compare the magnitude of the light coming from that. Compare the magnitude through a blue filter to the magnitude just through looking at the visual light. And remembering that smaller magnitudes correspond to brighter stars, this tells us that a smaller color index corresponds to a hotter object. For example, the sun, we take blue filter minus visual filter magnitude is 0.66. Rigel, a bluer, hotter star, has a BV color index of minus 0.03. And astronomers don't just use blue filter sounds arbitrary. They don't just use blue and visual filters. They use whatever filter is appropriate to a given star. So you can use a blue compared to a visual filter to establish the color of a star. You can use ultraviolet compared to blue for hotter stars. For less hot stars, you might compare visual to red filter, or even red to infrared for a really cool star. But any of these can be used to establish the temperature of a star. And so this is how astronomers do it, using one of these color indices. Any questions before I give you one last poll question before I send you on your way today? And here I'm also giving you an opportunity to look at the question because I want you to remember this mnemonic. An example being, oh, be a fine guy or girl, kiss me. All right, I'm going to ask you this poll question, which is, Sirius has a spectral type A and Rigel has a spectral type B. What can we conclude? Which one is hotter? And here you need to use the mnemonic. Just remember, which side of the letters corresponds to the hotter stars, which side of the letters corresponds to the cooler stars. This is going to do, if you learn this now, this will be very useful in the future, because in the next lecture, we're going to be continuing to talk about the color of stars quite a bit when we talk about the Hertzsprung-Russell diagram. Give you 10 more seconds. Okay, I'm going to end the poll. And so I'm going to share the results here. So most people got the right answer. Sirius has a spectral type A. Remember, it goes OBA. So O has the highest temperature, next B, then A. Okay? So B, Rigel, has a higher surface temperature than Sirius. Okay? B comes before A in this OBAFGKM carbon classification. Okay, so the answer was A. And remember, so C, for example, talking about core temperature, this is just the surface temperature. That's the only way we can see anything about stars is by looking at their surface, not their cores. Okay, and so next time we're going to complete this lecture by talking we're going to fit all these puzzle pieces together to talk about what's called HR diagrams. In one diagram, we're going to be able to see things about the luminosity, the temperature of stars, their size, how long they live, the things about their life and death. It's going to be really, it's all going to fit together, I promise. So any questions before I let you go? All right, everyone, I'll see you Wednesday. Thank you, Professor. Bye.
Thank you.
12:44.